hypothesis of Stokes. Not the question, but actually discussing the consequences of the hypothesis of Stokes. He said the first one is that the stress tensor is a function of the deformation tensor. We then defined the deformation tensor and saw what is the meaning of this. The second one is isotropic, which means that if you transform the coordinate system, we talk about an orthogonal transformation of coordinates. You're going from one orthonormal basis to another orthonormal basis. So the components of the stress tensor as well as the deformation tensor, both of them will change. But however, the functional relation between the components of the stress tensor on the one hand, that of the deformation tensor on the other hand, will not change. So what this means really is that if we talk about an orthogonal transformation, so L transpose is actually equal to L inverse. Can you please open the door? So what this means is that this indicates how the components transform under an orthogonal transformation. The matrix L really contains the dot product of the unit vectors in one basis set with that of the unit vectors in the other basis set. So this is how the components of a second order tensor will transform. So if the components of the stress tensor transform, and then correspondingly the components of the deformation tensor will also transform under the same transformation of coordinates, right? However, the same function which relates components, the stress tensor and the deformation tensor with the original coordinate system, that same function will determine how the components of the stress tensor are related to those of the deformation tensor in the new transformed coordinate system. The third one is that the stress tensor should reduce to that of the hydrostatic stress, state of hydrostatic stress, when there is no deformation experienced by the fluid. Now the net result of these three hypotheses is to show that then the stress tensor should have the following general form, which is given by. We are not going to give a proof of that. It's somewhat involved. Now, where alpha, beta, and gamma, we said, are scalar functions of the invariance of D. Then we started discussing what we mean by the invariants associated with the second order tensor. Of course, that we have to look at why alpha, beta, gamma can be allowed to depend on the invariance of D, because we are actually talking about things that do not vary when you transform. Right? So those also have to be a part of the general expression. The other question is also why we stop with D squared. Why not go on to D cubed and D power 4 and so on. So we give a rough outline of the derivation and explain some of these factors. For details of the derivation, you can refer to either Aris or the book by 7. So we now have to explain what we mean by invariance. So if you have a second order tensor and you have its representation in a particular coordinate system, it will be a 3 by 3 matrix, and I can formulate the eigenvalue problem associated with the 3 by 3 matrix. Then the eigenvalue characteristic equation, which gives the eigenvalues, will have the following form. Okay, so they can be written in this form using the same notation as used cubic in lambda for a 3 by 3 matrix. Now the coefficients, we have to prove that they are invariant under coordinate transformation. That remains to be shown. The coefficients can be easily verified for any matrix A, let's say, would be the trace of the matrix A. The coefficient of the lambda squared term would be negative of the trace. That's very easy to show. And the constant term in the polynomial equation will correspond to the determinant of A. We just expand out this equation. You should know how to determine the eigenvalues of any matrix, but this is applicable for any square matrix. You get additional terms. Well, of course, they also would be invariant. That's more difficult to prove probably. So you have to take the determinant of that as equated to 0. And then group together the terms. Clearly here, the way this is written, because I can also write it as lambda I minus A equal to 0. Then you will directly get coefficient of lambda cubed to be 1. Here, if you expand this, you will get the coefficient of lambda cubed to be minus 1 actually, directly. However, you can always multiply by minus 1, and this is what you will get. So the coefficients of lambda squared term would be the trace, and that of the constant term would be the determinant. This one, if we expand it out, you will get a certain form, but when you get in the compact forms, it's actually half times the square. I might have missed out the half factor if at all I wrote it in the last class, but it can be written compactly in this way. We of course know how to write the determinant, also can be written as so these are what I mean by the invariants. So invariants of D of course will have phi D if you're looking for the matrix D. And this would be the determinant of E. So this is what you would get. You have to show that these are invariant under coordinate transformation. So this is what you would get. And of course, it's also known one simple reason why we stop with these. This is the most general form of the relation between T and D, or rather this function f under these hypotheses. So we also know there is a famous theorem called the Hamilton theorem, which says that every matrix satisfies its own characteristic equation, right? So then we would simply have for a matrix A, this would now be a matrix equation. We simply get A cubed what? This will be A, and this will be I. This is our matrix for a 3 by 3. This is how we have, right? So clearly, you can see that A cube can always be expressed in terms of A squared A and the other terms. So even if you add additional terms, those can always be expressed in terms of the matrix and the invariants because of the Hamilton theorem, right? So that sort of explains why you need not have to consider additional terms. Right? Now we will simplify this further and impose additional restrictions, further simplification. I will now demand that T be linear in D. This is the furthest, this is the most general form we can get, but the non-linear terms are always more difficult to deal with. So consider a simpler class of fluids for which T is linear in D. This will lead to the very well known, linearly viscous fluid, or what is often referred to as a Newtonian fluid. Now, if I impose that, clearly this term would vanish automatically. Even if gamma is a constant, it can be a function of the invariants, right? D squared we cannot have because it's linear in D, so this will automatically vanish. So we are left with these two terms, right? So this would have to be there, but then beta cannot, because beta is a function of the invariance of D. If beta is a function of the invariance, then you will get a non-linear effect dependence on the elements of D. Because all the invariants are obviously dependent on the elements of D. So we have already a D here. If beta were to depend on the elements of D, then again the final expression for D will not be linear in D. So beta has to be a constant. Right, so we are left with this, and then we have the third restriction that D has to be this form, right? So what can you say about alpha? One possibility is to consider E equal to minus DI plus beta D. So beta is a constant now. Beta is a constant in the sense it can be a function of variables like a temperature, for instance. This will turn out to be the viscosity. That can be a function of temperature, but it is not a function of the properties of the motion. That's what we mean when it's a constant, right? It can be a function of state, the thermodynamic state. Now, that complication we are really going to consider for the major part of this course. So this is what we have. But if you now look at the invariants, this is not the most general form, because this is whatever comes here will be multiplied only by I, right? So now if D is to linearly depend on D, certainly these are ruled out. The constant, the alpha cannot be a function of the second and third invariant, but however, this is linearly related to the elements of D. So alpha can be a function of the trace of D. The most general form is not quite this, but I can write this as minus B plus lambda times I plus, and I will simply call the beta to be twice a quantity mu, which is what we know as the dynamic viscosity. I'm just replacing beta by 2 times mu. That is what it would turn out to be. What we measure as viscosity is actually beta divided by 2. Right? So I'll just introduce that. So the lambda is the additional quantity. It is not quite the bulk viscosity, but it is also can be termed as a viscosity. Right? Now, if you look at what the first invariant, the trace of D is, what is the trace of D? It is dii, that is d11 plus d22 plus d33. So what is d11? We have to know, go back and think of what is the formula for dv1 by dx1. It's the symmetric part of the velocity gradient tensor. Now the velocity gradient tensor, where we will have dv1 by dx1 as along the diagonal. Other elements, right, will be there. Now the symmetric part will be half times this plus the transpose of this. So you can easily verify, because the antisymmetric part will have all diagonal elements 0. The symmetric part has to have the diagonal elements which are the same as the original matrix, which in this case the velocity gradient tensor. Right? So clearly this is dv1 by dx1 plus dv2 by dx2. This is clearly the divergence of the so I can replace this by further here for a linearly viscous, so this may be what is called as a linearly viscous fluid. But this is not all. We can consider two types of linearly viscous fluid. One a compressible linearly viscous fluid and an incompressible linearly viscous fluid. So we consider an incompressible and a compressible. So there is a big distinction between the two. You have to understand that very clearly. I will explain what I mean by incompressible fluid. The incompressible fluid is one for which the density is a constant identically. It means whatever motion that the fluid may undergo, its density is not going to be a function of either position or of time. That's an incompressible fluid. Now if you look at the equation of continuity of the incompressible fluid, the equation of continuity in general we have defined without any reference to any particular type of fluid is this, right? If the rho is constant, then this is 0. This rho can be taken outside, so that means for an incompressible fluid, this will be the continuity equation, right? And what about the momentum equation? That would be rho. Of course, for t, I have to now substitute whatever I have there, right? But important thing to know is that now clearly, even if we directly look at this equation, obviously this will be 0 for an incompressible fluid. So for an incompressible fluid, I will get this very simpler looking expression. Now for a compressible fluid, right? So this I can retain from a compressible linearly viscous fluid. Although it appears that the equation for the incompressible fluid can be obtained from that of the compressible fluid by simply taking the divergence, the velocity field to be 0, which is what it is. However, there is an important difference. If you look at the equations for the incompressible fluid, the density is no longer a variable of the motion. So, earlier we said I have 4 equations for the 4 fields. One is the density field, which is scalar field. Another is the 3 components of the velocity. So there are 4 variables, 4 equations. Right? So now the density is a constant, it has to be specified. It becomes a parameter. You have to specify what that constant density is. It's no longer to be determined by the equations continuity and motion. So then we seem to have 4 equations but only 3 variables. However, it's important to remember that the pressure is no longer a thermodynamic variable, which it is for the compressible fluid. That's the important difference. So the pressure becomes now a mechanical variable to be determined from the equations of motion. Right? So here, incompressible fluid, P is a mechanical variable of motion. So what about compressible fluid? The compressible fluid, P is a function. P is given by an equation of state. So the compressible fluid P is equal to some function of rho and T. So it depends on the density and temperature. Whereas for the incompressible fluid, the pressure doesn't, the density itself is a constant. So the question of the variation of pressure with density doesn't arise. The pressure becomes a variable to be determined by the equation of motion. Of course, you have to solve the equation of continuity together with the equation of motion in many cases to get the pressure. Right? So you'll see the exact meaning of this later. But this is an important distinction that you have to, although in principle, the equations for a linearly viscous incompressible fluid can be obtained. We'll see later on very clearly. From those of the compressible fluid by simply making the divergence of the velocity field zero, there is an important difference in that the pressure is not an independent variable in the case of the compressible fluid. It is given by a local equation of state, right, which depends in general both on the density and the temperature. We've seen P equal to function of volume and temperature in thermodynamics. It's an equation of state. But in terms of the incompressible fluid, because in effect the volume doesn't change, or the specific volume doesn't change, there is no effect of the pressure on the density because it doesn't change. So the question of an equation of state doesn't arise. So the pressure is not a thermodynamic variable to be determined by the equation of state, the mechanical variable to be determined by solving the equation of motion along with the equation of continuity. Right? So that will come out clearly when we write these out in Cartesian or any other coordinate for the linearly viscous and the linearly viscous compressible and the linearly viscous incompressible fluid. We will see that clearly later on when we solve specific problem how the pressure is to be handled. Are there any questions on this? Yes?
So how did you get
Huh? No, I am just replacing the beta by 2 times mu. Because what we know as the viscosity turns out to be simply beta by 2. I just introduced beta as an arbitrary coefficient. It doesn't have any physical meaning here. But we all know what the viscosity is and how it is measured. Right? It's a physical quantity associated with every fluid. It so happens that that viscosity simply turns out to be beta by 2. So I am just replacing the beta by 2 times the viscosity. If you want, you can leave it as beta. Right? That is what it is. Yes?
So if you could understand why you are added the term lambda into that.
Yeah, because the alpha, right, can be a scalar function of the invariance of D in general. That is in general. So it can be a function of this as well as that. But now when I am restricting to a linear fluid, that means D is linearly dependent on D, right? So this alpha, right, cannot be a function of this and this because the tensor multiplying is a unit tensor, it's a constant. So alpha is just a scalar function of any of these three. But if it's a linear fluid, this also has a non-linear term. This also has a non-linear term. So it can depend only on this. So I am introducing that. If I leave it like this, then it's not the most general form. Because alpha can depend on an invariant. For a linear fluid, the only linear invariant associated with D is the trace. So it can depend on the trace. So I am just multiplying it by a constant coefficient and introducing it in that way. Right. So the fact the third hypothesis is satisfied, as I erased it, the third hypothesis is still satisfied. But when D is equal to 0, that doesn't affect the third hypothesis. It It has to be consistent with all the hypotheses. When D is equal to 0, that means all the elements of D are 0. That's the state of no deformation. Right? In that case, clearly the trace of D is also 0. Right? So, this form, as well as this form, reduce to the state of hypostatic stress when D is equal to 0. Clearly, compare these two. The more general form is this. So I have to allow for this. When we talk about the most general form consistent with Stokes' hypothesis, the additional restriction of a linear relation between E and D. Right? So in that case, I have to have this term. However, for the incompressible fluid, that term is anyway 0. So I am left with just this.
So is lambda dilatation of viscosity?
Yeah, we will take a look at that later. It is related to the lambda plus 2 mu by 3 will be the bulk viscosity. It is often taken to be 0. For all practical purposes, lambda can be replaced by minus 2 mu by 3. It is what is done. But most textbooks do not teach it solving equations involving compressible fluids. So this doesn't become a big issue often. You look at that later. That's not quite exact. That's called as the Stokes relation. It is not believed to be generally true. We will come to those complications later, because first I want to solve this assignment sheet that is given before we get into the details of particular types of fluids and what these coefficients mean. Are there any questions? No, that because we are looking for the most general form consistent with the Stokes hypothesis turns out to be this. Now I am imposing that D has to be linearly related to D. So alpha can depend, since in general it can depend on all the invariants of D, but for a linearly, for something where D has to be linearly related to D, it can depend only on the trace. So this is only for a linearly, what is called as a linearly viscous fluid. So we finally arrived at what we are going to use, and that is importantly, I should also write here that D is equal to a function as given by the equation of state. That's a very important thing you have to keep in mind. Because on the face of it, if I put del dot B equal to 0, that is the divergence, I get this. Right? But there's another distinction between the compressible and the incompressible fluid. And the way you can approach the solving of the equations will be somewhat different. Because the pressure has to be solved for in the case of an incompressible fluid.
So pressure is a function of density and temperature.
Yeah, but
Because T and T is confusing a little.
oh, okay. Yeah, temperature. This will not come in very important here because the first part we are going to deal with only the, but that is a tensor, this is a scalar. We have to live with that. I don't think there will be any confusion effectively. Any other questions? The important thing is that there is a theory behind these equations. These equations arise out of the principle of conservation of mass and the momentum, principle of momentum balance, right? But what happened to the person who was sitting at the back? Left, is it? Looks like I have to take attendance a second time. Mr. Ankit Kumar here, when he uses the attendance, he will inform for both classes. The person who is sleeping, don't disturb him. He's not Ankit Kumar, right? No. As long as he doesn't disturb me. So what I want to point out is that the equations of motion and continuity, they are part of a theory that is very well understood. These form the foundations of fluid mechanics. However, this is what may be called as a constitutive equation, in that it depends from fluid to fluid. How the stress would actually be related to the properties of the motion is not a universal relationship. Already seen that this is very, very special. First, I want you to see how special this is. This is what will lead to the famous Navier-Stokes equations. And often it is regarded that the Navier-Stokes equations are the most fundamental equations in fluid mechanics. They are not. The Cauchy equation of motion are the most fundamental equations. Depending on what type of fluid you deal with, you will get different relations between T and D. Or in some cases you might even have to, this is again limited set of proposals that Stokes came up with that leads to further specialization to a linear dependence is what gives this. So you can see how special the Navier-Stokes equations would be. They certainly cannot deal with what are known as non-Newtonian fluids. Right? But what I also want you to understand is the so-called constitutive equation. The important contribution of Stokes is that there is also a theory behind this. The three hypotheses that we have listed, right, that the stress has to depend on the deformation tensor and the invariance with respect to the transformation of coordinates and the reduction to the hydrostatic stress. These are the principles that Stokes formulated so that you have a general theory of constitutive equations, within the context of which you can look at special cases and particular types of fluids. Right? So that is what I wanted to understand, that there is also a principle behind the Newtonian fluid which leads to the equations for the Newtonian fluid, and those principles are what Stokes laid down. They are not simply obtained by merely empirical means or just experiment alone. There is also a theory behind it. That is what I want you to understand. Let's start solving some of these assignment problems. Let's take problem 2. We're not going to consider problem 1. These will further illustrate the significance of the deformation tensor and the invariance. So, what I am having here is I want you to show the physical significance, I will understand the physical significance of the diagonal and the off-diagonal elements of D. So, what I have asked you to prove is that consider two material points which at time T are separated. So, this is the coordinate system I have chosen, because we said how did we arrive at this important relation d by dt of ds squared plus 2 dx whole thing is a vector. Almost made it using e of the vector x. So what we considered was the physical significance of this was that I said let's consider two material points. We characterize material points by the material coordinates. Right? So now at time at a particular time t, this is at some reference time, we're not really worried about it, some instance of time. So this is moved to x, and this is moved to what I will call x plus dx. Right? So the dx is really the vector connecting x and x plus dx. This is the vector dx. Now the length of this vector is given by square of the length is given by d square. And that is what this gives, the relation. At that time many of you ask the question, why not directly take the time derivative of dx1 and dx2 and so on, why take the square? Right? This gives us this is a very compact and somewhat simple relation to remember. Now what I am saying is, consider the dx to be oriented in the along the O1 direction, and then you see what happens to this formula. Right? So what I am saying here, forget about where this comes from. Finally focus at time t. This is the dx, let's say. It's oriented along the E1 direction, but it has a length equal to dx1, right? So now, can you come to the O and write what the left hand side would be? D by dt of what? Now what would happen to ds squared? For this particular case, the dx is given by dx1 times e1. Yes, so what is that? You don't have to, don't put a vector on everything. Please, you realize what you are writing. The dx1 is the length of that vector pointing in the e1 direction, so I've written it as the scalar dx1 times e1. No, fine. I wanted you to write what is the left hand side. You not just leave it like that. What is that dot product? Is it so difficult to evaluate what the dot product is? Huh? dx1 square, that's all. D by dt of dx1 square. Okay, what can you say about the right hand side now? Yes, dotted with dx1 e1. Yeah. How are you going to evaluate this? Unfortunately, the way it is written is not that straightforward to evaluate, but if you look at the general expression that we wrote, this is after all a scalar. We've already written this form, right? We did dx dotted with d. The ith component of that is dxj, dji. Then I take the ith component of that is a further dot product. Final result is a scalar. Now you tell me, looking at this, what would this be for dx equal to dx1 e1? There are 9 terms in this sum. I equal to 1 to 3, j equal to 1 to 3. How many terms will actually count? 6 terms. 3. three terms. So we write the, can you write the three terms? Yes, but what is the, there are so many other terms also. Why did you write them off and why are you writing these terms? Yeah, fine, but what is dx2? Huh? Yeah, so just one term out of the 9 terms will survive. You can easily expand it out and see, because dx is just this, that's the important thing. Basically dx1 is dx1, right? So dx2 is actually equal to 0. For this particular case I am considering dx3 equal to 0. Whichever way you look at it, now I can expand this 2 times. Let's take j equal to 1, right? So dx1. So j equal to 3 are going to give me 0 for dxj. Since this is a product, right? I get only this term. Now what are the terms you said? Correct, 3 terms. This would be j equal to 1, d11 dx1 plus d12 dx2. Again this is 0 plus d13 dx3. This is also 0. The particular dx I am considering, dx2 and dx3 are 0. It means I am considering an element of fluid oriented in the around the O1 direction, right? So the net result is d by dt of that particular case. The time rate of change of the length, square of the length, will simply be 2 times d1 dx1 squared d11. That's all. So only the first diagonal element of D will be picked in this sum. All other terms will simply have 0 contribution. You have 9 terms involving all the elements of D. Only D11 will be picked, right? So that is what it is. So this would be d by dt of dx1 squared can be written as 2 dx1 right, is equal to 2 dx1 squared d11. When you get rid of the 2 and you get rid of one of the dx1s, and I get this striking relation. So what can you say about the right hand side? What does it represent? Because the length here is only dx1. So this is the time rate of change of the length of that element per unit length. Right? So that is why sometimes the deformation tensor is often referred to as the rate of strain tensor. May be regarded as a rate of strain change in length, in elasticity. Right? Often it's a strain, you've heard of stress strain relation. Of course, the Hooke's law is the simplest case, the one-dimensional case. You have to consider more generally three-dimensional case. Typical constitutive relations in elasticity relate the stress to the strain, whereas in fluid mechanics, it is the stress related to the rate of strain. This is one way of interpreting. In a similar way, if I now consider, right, dx, this is case 1. Consider dx is equal to case 2. E2, and then case 3. Dx is equal to dx3, E3. In general, dx can have any orientation. It can have components dx1, dx2 and dx3. In which case I will get this entire sum, which involves actually all the elements of D. But by picking a particular element which is oriented along the O1 direction, I am able to give a physical meaning for the diagonal elements of D. Clearly, this would lead to D22, to be 1 over dx2, and so on. So D11 can be regarded as a time rate of change of the length of a fluid element that is oriented along the O1 direction per unit length of that element. D22 can be regarded as the time rate of change of a fluid element oriented in the O2 direction per unit length of that element. And D33 can be similarly regarded, right, as the time rate of change of a fluid element oriented along the O3 direction per unit length of that element. So it's like a rate of strain. Are there any questions? The algebra involved in this is fairly straightforward, but the final result is somewhat significant. It gives a physical meaning for at least the diagonal elements of D. Now we have to look at what the off-diagonal elements of D mean. For that I have considered now a more general situation. That will be part of the subject of assignment problem number 2, the segment B, subsection B. We will consider that now. So here what I am considering are actually 3 material points, because the off-diagonal elements will be related to the rate of change of the angle between two elements oriented along the coordinate axis.